Hello everyone and welcome back. In this tutorial session, we will cover forces in the space. And in this video, you will know that the force we are in the space has three components. A component in the x direction and y direction and z direction. And we'll show you how to get the resultant of different forces acting at one point, and also if they are in equilibrium, how we can solve the equation of equilibrium, which means that the sigma forces in the sigma component in the x direction should be equal to 0, and sigma component on y direction should be equal to 0, sigma component in z should be equal to 0, and how also like if to get the component from the beginning once we know either the angle, the direction, or if we know the 2 points on the direction of the force in the space. So let's move forward. So if I have forces in the space, first I would like to find out how to get the rectangular component of a force in the space. So now let's look at the space we have. If you look carefully here, like we have the direction. We have x direction and y direction and z direction. And say I have a force F is going from O to A, and this force I draw it inside a rectangle parallelogram. So this way we can identify the value of x's and y's and z and so on. So this force in the space has three components. What are these components? They are the component in the x direction, we call it f of x. Component in the y direction, we call it f of y. And component in the z direction, which we call it f of z. So now to determine the x component or the y component and z component, we need to know the angle between the force and the x-axis. So in this case, if I would like to get the fx, the component in the x direction, you multiply the force by cosine the angle theta x with the x-axis. Similarly, we will do the same if we have a force in the space. What about the y component, the fy, the y component of the force? Then I have to know what the angle between the y-axis and the f force. So this you multiply the force by cosine theta y, you get the y component. Again, you repeat it for the z direction. So if you know the force, which is theta z, which this angle here, so theta z, you multiply f by cosine theta z, you get the z component. So now once you know the component, so what I can do is I can represent now the force, the total magnitude, the total force as three components: f of x in the I direction, f of y in the j direction, and f of z in the k direction. I is a one unit vector in the direction of the x-axis, j is another one unit in the direction of the y-axis, and the k is one unit in the direction of the z-axis. Just to identify I, j, and k when you write it in the equation, so you know what component are x's and what the component in the y direction and what the component in the z direction. So we add this term. And as you know, as you find, as I mentioned earlier, that the x component of the force is equal to what? F cosine theta x. Y component is equal to phi of f cosine theta y. And similarly, the z component is equal to f cosine theta z. And to get, just in case, if we have the component, can I get the force? Yes, you can do by getting the square root of the f of x squared plus fy of y squared plus f of z squared. So this way, when you get the square root of that, you will get the force f. Okay, what else? There is a relationship among these. The cosine theta x, we call it direction cosines. So these cosines, we call it direction cosine. But there is a unique relationship among all of them, which mainly is cosine square of theta x plus cosine square of theta y plus cosine square of theta z. They are all equal to 1, no matter what this force. If you did the component, you should get this relationship. So now let's move forward to see what is the other condition. So the other condition is if I have a force defined by its magnitude and 2 points on its line of action. So if I have the axes, the coordinate axes, x, y, and z, and then I have a force F, and this force is defined by magnitude F, and a 2 point A and point B are in the direction, are located on the line of action of the force. So I know the force F1, the force 1, the point 1 and point 2. So if I'm going from 1 to 2, so this is the direction. I'm going from 1, I start from 1 and I end at 2. Okay, so this is a force magnitude by F and is going from A to B. So how we can determine that this the component of this force? To determine this component, we need to calculate what? The amount of displacement, the amount of motion in the x direction, and the amount in the y direction, and the amount of distance in the z direction. How we get that? It's just you subtract x2 from x1, you get the dx, y2 minus y1, you get dy, and z2 minus z1, you get dz. So now once I get dx and dy and dz, then the next step is to calculate the total distance from A to B. And the total distance from A to B is equal to what? Equal to the square root of, so the distance D is equal to the square root of dx component square plus dy component square plus dz component square. So once you determine that, I determine delta D, and then the next step is to determine the vector lambda. The vector lambda, we call it the direction cosine vector. This is a vector. If I multiply by the magnitude of the force, it gives me the x and y and z component of the force along the x and y and z coordinates. So actually is, so we multiply the force by lambda, and the lambda is 1 over d. So you multiply the vector dxi, dyj, dyj, and dzk, divide by d for all of them, then you multiply by the force F. F is a constant, so it becomes F over d. So these are two constants, but I can, so F over d multiplied by dxi, dyj, dzk, so I can get the value of the force. When you do this multiplication, you end up with the x component and y component. Just to explain lambda, lambda is a unit vector, because once I divide by the value of d, so lambda becomes like a unit vector in the same direction of the force. Okay, so means that dx divided by d is considered cosine theta x. dy divided by d is considered cosine theta y. And dz divided by d is cosine the theta z. And this is what we get from the relation. So this is f of x component. You can get it either by theta x or cosine theta x, or f multiplied by dx over d, fy, f dy by d, fz, f dz by d. Okay, where is the cosine direction? Cosine theta x is equal to what? Dx over d, cosine theta y, dy over d, cosine theta z, dz over d. So now let's move to the two applications we're going to cover for today. First, we're going to see how we can add forces in the space at a certain point. So the first step is to determine the x component and the y component and the z component for every force. So for every force, determine the x component and the y component and z component. Then the next step is what? To determine the resultant component. Means I need for the resultant of x in the x direction is going to be all the summation of all the fx component. The resultant y in the y direction, the component of the resultant in the y direction is going to be equal to what? All the forces in the y direction. And the resultant force in the z direction will be all the forces or the component in the z direction. Once I know Rx, Ry, Rz, now the next step to get what? To get the resultant. So the resultant will be the square root of Rx, R square x plus ry square, ry square plus rz square, the whole thing under the square root, you get the value of r. And you substitute it into this equation, you get the value of r. Now, so this way I calculated the resultant force. But this is as a magnitude. How can I calculate the direction of this force? So to determine the direction cosine of the resultant force, you need to get the cosine theta x, cosine theta y, and cosine theta z. So the first one is going to be rx over r is cosine theta x, ry over r cosine theta y, rz over r is cosine theta z. So this way I was able to get the resultant of forces acting in the space at a certain point, magnitude and direction. The next case is to solve equilibrium. Forces acting at a certain point in the space, but they are in equilibrium. We'll repeat the same methodology or same procedure. For every force acting at any point, let's resolve the force into what? It's a rectangular component. Means for every force, I'm going to calculate f of x, f of y, f of z by following the same procedure of creating the lambda vector multiplied by the force in this direction. So I get the fx, fy, fz. Then the next step is what? To apply the conditions for equilibrium at this particular point. And what's a condition of equilibrium? Is all the summation of the x component of all the forces should be equal to 0. All the summation of the y component of the forces should be equal to 0, and all the summation of the z component should be equal to 0. The first example is this problem here. I have a tension in cable AB, so cable AB has a tension, and this tension is 10,000 Newton. Determine the x, y, and z component of the force exerted by the cable on the angle B, and also would like to determine the direction cosines, the cosine of the angle, which means the angle theta x, theta y, and theta z, defining the direction of that force. So what's given is given the tension in AB. So means mainly is, if I look at this one here, I have a tension here at B is going up in this direction, and now we need to resolve this force. We need to get the resolve of this force into the component. So we're going to have like a vertical component in the y direction, a component in the z direction, and a component in the x direction. It's going to be this way. So actually this will be the tension. This will be the tension in AB, and this will be the y component, the x component, and the z component. Okay, the first step number 1 is what? Is to determine the position of A and B. So if you look at point A, it is located at the y coordinate. This means that it has a 0 coordinate for the x and a 0 coordinate for the z, but for the y it has what? The value 18, and it is in the positive direction. So I get the current axis of point A, which is the x value is 0, the y value is 18 positive, and the z value is 0. Now let's go to a point B. So for point B, it is x is going to be positive. How much is 12? So 12 positive. And then the y is 0 because it is located in the plane. And then the z value, it is in the opposite side, so it's going to be minus what? Minus 9. So the first point, the first step is to determine the position. So this is what we have. We have what? We have the 0x for point A, 0, 18, 0. And the point B is 12, 0, and minus 9. Now, the next step is what? To determine the vector lambda. So to determine the vector lambda, first we need to get the dx value. So it's going to be ax minus, so I'm going from B to A. So the final point is A and the starting point is B. So it's going to be A minus B. So it's going to be 0 minus 12. 0 minus 2 is going to be minus 12. And then 18 minus 0 is going to be a positive 18. And then 0 minus 9 is going to be what? 9. So finally I got the value of dx, the value of dx, dy, and dz. Okay, by what? Subtracting point B from point A, because point A is the second one. Okay, once I got dx, dy, dz, so I substitute into the equation to calculate the total distance AB. So by here, so this distance here is what? Is the length AB. So I calculated the distance is going to be what? The minus 12 square. So I got the 3 point here, the dx. So this one here, and this one here, and the third one is here. So under the square root, and you get the total distance is d is 23.43. So I got the dx, dy, dz, and I got the total d. So now let's do that, the lambda. So the lambda will be what? That the equation is 1 over d multiplied by the vector dxi, dx, dy, j minus plus dzk. Okay, so this is a vector based on the dimension dx, but I normalize it by dividing by the total distance to make it the cosine values. Okay, so this way I got the dx over the total distance d, dy over d, dz over d. So let's go back again here. So dx is minus 12. So minus 12 over 23, I get minus 0.5, and then the next one here is going to be what? 18 over, so this one actually is what? Is minus 12 over what? 23.43. And this one is what? Is 18 over 23.43. And the last one is what? Is 9 over 23.43. Okay, so I got all the lambda vector. Once I get the lambda vector, I multiply it by the force. The force I have is TAB is what? Is this value here, is the value 10,000. So okay, so the next step is to multiply. F is going to be F multiplied by lambda. So I have F is 10,000, the force, multiplied by the lambda vector. So I normalized lambda vector by dividing by 1 over d, and I put the component. So now I have the 3 components. So this way I calculated, I did the multiplication. So I found that this value will be what? The x component. This will be the y component, and this will be the z component. As you can see, the x component are in the negative direction, the y component in the positive direction, and the z component in the positive direction. And this is how I calculated the 3 component by just applying the methodology. Now in part B, we need to calculate the cosine, the angles theta x, theta y, theta z. We know that from the equation that the lambda vector is represented by what? So the lambda vector is represented as this vector here. So from here, which is cosine theta x in the I direction, cosine theta y in the j direction, cosine theta x in the k direction. Or in another way, you can say lambda or cosine theta or cosine theta x is what? Dx over d. So we already did that. So what we're going to do is just, so what we're going to get from here is theta x is going to be what? Cosine minus 1, the value. So this is why from the lambda vector, I'm going to go to theta x is going to cosine minus 1, the first term. So it's going to be negative minus 0.5122. So it's going to be, this is why you have to put the negative because you need to get it correct. So it's going to be 120 degrees with the x-axis. The other one is the theta y is going to be cosine minus 1. You apply the rule, just cosine minus 1 is what? The second term. And okay, let me use different color. So theta y is going to be with this term here, and theta z will be with this term here. Okay, so cosine minus 1 of 0.3841 and so on. So once we got these three values, so I was able to get the theta x, theta y, and theta z. Okay, as you can see, it's the systematic work. You need to follow the procedure and the thing, and be careful when you decide about the coordinate axes of each point and so on. Straightforward.
The second example in this tutorial is a problem about how to use the equilibrium conditions to determine the forces. In this case, we have a balloon. This balloon is tied at point Q by 3 cables. So there is if you look at the space diagram and compare it to the free body diagram, I have a force P acting on the balloon vertical, and then I have a tension in the cable QB, tension in the cable QA, and tension in the cable QC to hold it down. The condition given is that the tension in QB is 500 newtons. So give me the magnitude of the cable. So I know the magnitude and direction for cable QB. I know the direction only for QA, and the direction for QC, and the direction for P. So now we need to determine what are the tension in QA and QC. So just for your information, we found that the force P is vertical, so it means that it has 0 component in the x direction and 0 component in the z direction, and the total force P is in the y direction. So this is why we wrote the equation of the force equation as 0I plus Bj and 0k, and we call it this equation number 1. We're going to use it later. So now the methodology of solution is very straightforward. So we have the free body diagram. Here is the space diagram. Now we need to determine what the position of all the points and length. So and determine the length from that. So determine all the position. So we look at point Q for point P, for example. So at point B, if I want to know what the condition of the point P is, the location of point B, what is the value of x? It is located on the axis z, means what? The value of x is 0, the value of y is 0, the value of y is 0, and then the value of z in the negative direction, which is what? Minus 4.2. And as you can see, we wrote this dimension here. The point B is what? 0, 0, minus 4.2. Okay. Now let's get the point A. Point A is located at the x-axis. Means what? Means y, the x value is the 3.3. I have 3.3 here. Then the y coordinate is 0. And then what? The z values is also 0. And this is, we have the point A here. I listed here under the position of all the points. Now the third point is point C. And as you can see here, minus 4.2, minus 4.2. The y component is 0. And the z component is what? Is positive 2.4. So 2.4. Okay, so we wrote the values for the point A, C here. Minus 4.2, 0, and 2.4. So we got all the 3 point A, B, and C. Now we need to get the component, the coordinate for point Q. Coordinate is located on y-axis, so now is the x is 0 and the z is 0 and the y is what? The height is 5.6, 5.6. Okay, so now you go back here and you find that point Q is 0, 5.6 and 0. So we determine all the coordinates. This is the most important part, is determine the coordinate of each point correctly. So we got point B, we got point A, we got point C, and we got point Q here. Okay. So once we determine the point, we'll move to the next calculation, which is what? To determine the length and the lambda vector. So now we're going to start by one cable at a time. So we'll start with cable QB. So first we're going to do what? B minus Q. So it's going to be 0 minus 0. You got the x component. And then what? 0 minus 5.6. You got the y component. And this one, then what? Minus 4.2 minus 0. You got the third component. So now I got the vector in the direction of the tension QB, which is what? 0I minus 5.6 minus J minus 4.2K. But I need to normalize that. So I need to calculate the distance QB. So the distance QB is what? Is dx square plus dy square plus dz square. Now, the first is going to be what? The first item here is going to be square. And then the second item here is square. Plus another third item here is square. So it's going to be 0 square minus 5.6 square minus 4.2 square under the square root. You get the distance QB is what? Is 7. Now to get the lambda vector, you divide this vector. I got this vector here by the points by 7. So you get the lambda vector. So the lambda vector will be 1 over 7 of what? Of this vector here. So we're going to put this vector here. And you divide by 7. So you're going to be 1 over 7, 0I minus 5.6J minus 4.2K. Then the next step is what? To calculate the vector QB, which will be the value TQB multiplied by the lambda vector. So the value, okay, so the value is the 500, it was given 500. So this is TQB is given, which is 500. And then what we have? We have the lambda vector, which is 1 over 7. So mean 500 over 7 multiplied by the vector. So I get, when we do this multiplication, you get the x component, the y component, and the z component of the force of the tension QB. So it means that I got the x component 0 minus 400 minus 300 for, for the tension QB. We will repeat the same methodology to determine what? QA. So QA is going to be what? A minus Q. If you look here, I have A and I have Q. So 3.3 minus 0 is going to be 3.3 minus 0. And the next one will be what? 0 minus 5.6. 0 minus 5.6. And then what? 0 minus 0. And 0 minus 0. So you will get the vector what? 3.3i minus 5.6j and 0k. Now we need to normalize this vector. So we're going to say you get the square root of the first term square plus the second term square plus the third term square under the square root. So you get the distance QA. Then once you divide this vector, the vector QA, by the value of the QA, which is 6.5, you get the lambda vector. So now the lambda vector will be what? 1 over 6.5 multiplied by the vector 3.3i minus 5.6j 0k. Now you multiply by the tension QA, and we'll keep it. We don't know the value of tension QA, so we're going to keep it as it is. So it's going to be TQA, but we will calculate the other number. So it's going to be what? 3.3 divided by 6.5, so it's going to be 0.51 in the I direction, and minus 0.862 in the j direction, and 0 in the k direction. So I got the equation for the tension in QA. So we have the 3 component by multiplying TQ by these lambda vector. So the next step is what? Is to determine the last tension, QC. So the same methodology, we're going to go to point C minus Q. And in point C, you have minus 4.2 minus 0, so you get the first one. And 0 minus 5.6, you get the second one. And 2.4 minus 0, you get the third one. So you got the vector. And then under the square root, you take every item here. You square it under the square root, you get the distance, which is what? The QC distance is 7.4. You divide by the distance, you get the lambda vector. You multiply the lambda vector by the TQC, you get the component. So this is why you got TQC multiplied by minus this normalized value, minus this normalized value, plus this. This is the unit vector in the QC direction. So now the next step is what? I have all these four equations. So I'm going to summarize them into this table here. So if you look at equation 1, what I have 0, P, and 0. So you see, okay, the first P for the P value is going to have 0, P, and 0. So the X component, the Y component, and the Z component. Then the next equation is going to be 0 minus 400 minus 300. So, okay, 0 minus 400 minus 300 for TQB, which is a given one. Now we need the third equation, which is now the third equation is what? Is this one here. So TQA. So I have TQA multiplied by 0.51, 0.5 TQA, and then the next one is what? Minus 0.862 TQA, and the last one is 0 TQA. And then the last equation, equation number 4, is going to be TQC minus 0.5676 multiplied by TQC, and then minus 0.7568 TQC minus, and then plus what? 0.3243 multiplied by QC. Don't forget the QC here. Okay. So now I listed all the components in the X direction and Y direction and the Z direction. So now we need to determine which equation we're going to start with. Should I start? We have to apply the equilibrium condition. The equilibrium condition, we know that all the component in the X direction equal to 0, and the summation of all the component of Y direction should be equal to 0, and all the summation of Z direction and the component in the Z direction should be equal to 0. But which one we should start with? If you look carefully here in this column here, in the Z column, I have only one unknown, and then the second column I have 3 unknown: the P, TQA, TQC, and in the third column I have 2 unknown, QA and the QC. So I will start first with the first the Z column, because there is only one unknown. So we're going to say what? 0 minus 300 plus 0 plus 0.3243 TQC should be equal to 0. So this is what we have: 0 minus 300 plus 0 plus 0.3243 QC equal to 0. So from here, I have the only unknown is TQC. So I calculate TQC, and we got TQC to be equal to this. So I was able to get this value here. So once I got this value, I'm going to go to next to what? To sigma forces in the X direction. Why? Because I know TQC, QC, the tension in QC. So now it become only one unknown. I need to determine the tension in QA. So we're going to go and get the equation from here. 0 plus 0 plus 0.5 TQA minus 0.5676 TQC equal to 0. So this is the equation. So now we're going to substitute for TQC by 925. So I should be able to solve for TQ. So you solve for 2Q. So this way here, substitute for TQC, which is what? 925. So I got this one. So now I can calculate for TQA. So I get TQA. Now I know TQC and the TQA. So I will look at the third the Z. I'm going to look to the Y component. So sigma Y component will be what? Sigma Y component equal to 0. So it's going to be what? And substitute for TK tension in QA and tension in QC. So what we're going to have? We can have what? P minus 400. So P minus 400 minus 0.862 TQA minus 0.862, and here is QA. QA is what? Is 1029. We got it from the substitution here, and then 0.7568 multiplied by TQC, and we have TQC 920. So this is what T. So this is TQC, and this is what TQA. So substituting for these values, I get what? The force P. So now I succeeded to get the force P on the balloon. So as you can see from this example that it's a systematic approach. The most important part is to determine the position of each point in the space, and you calculate the lambda vector for each link or each cable, and after that, once you get you multiply by the value of the force in each for each force, and then you calculate the component, the x component, y component, and z component, and then you solve the condition for equilibrium, which mainly is sigma forces in x equals 0, sigma forces in y equals 0, sigma forces in z equal 0. I would like to thank you for watching the video, and I would love to hear your feedback. And please, if you like the video, please subscribe to the channel, click the bell, and give it a thumb up. Have a wonderful day, and see you soon on another video. Bye-bye.